let's discuss the homework. We have the upcoming homework, homework 7, which will be the heat equation implemented with the spectral element method. And we have the past homework, homework 6, which is the same equation, the 1D heat equation, but implemented with the finite element method. So what do you prefer? Shall we discuss first the finite element, then go to the new homework? Shall we do that?
Yes.
Good. So in terms of the homework 6, then you have the solution. I put that down into our Dropbox folder to share. The PDF, I can quickly show you that, and we can go through it quickly. Would look like this one. So here we have the problem set 6, the solution to it. It starts again with stating the initial equation, the diffusion equation, which for this home set is time dependent. So it's the unsteady state diffusion equation. And then the boundary condition and the initial conditions. And then it continues with the steps that we need for the finite element approach. So it discretizes it to finite elements. We have the function expansion into onto a new basis, which is the shape functions. And then we have this linear system, the matrix form that we set up. And for that, we use a mapping to this local element or the reference element. And for the mapping, we also use the same shape functions, which is very common in finite element approaches. That the shape functions and the basis function where you do the function expansion is the same. And then we have these local contributions. So here it's written out for the mass or the capacity matrix. So on top you have the global mass matrix or capacity matrix and stiffness matrix K, A, B, and the force or the right-hand side vector. And then on the local level, what are the local contributions on each node or for each element in principle? And you have them here written out, these expressions like this one for the capacity or mass matrix, the local contribution for the stiffness matrix here, and the local contribution for the right-hand side vector, the force vector, are written down here. So once we have these local contributions, then the third step is basically the assembly into these global matrices again. Just trying to make sure that we add all the local contributions onto the right global nodes, global positions. And for that, we have, for example, this location matrix, which tries to make that mapping of the indices. And then we basically solve the matrix form just with the linear form. From your side, what I saw in your solution, they all looked okay. So with these steps that you do, sometimes you can play a little bit around with the local contribution where you want to put these factors in. But then at the end, with the assembly together, it looked all okay. So we had these kind of solutions that we had. for example, for the a simple harmonic function that we used in the problem set A, and B was about the half-space cooling problem set. Where you can play around with the number of elements, for example. And you see the more elements you add, the more degrees of freedom or unknowns we have. And also the closer the approximation becomes. Good, so this is just an increase of elements leads to an increase of the accuracy. Right. Something I wanted to quickly point out, I'm not sure if I can do that in the code when we solve the linear system of equations. Let me quickly stop here. You have something to question about this part? What I would do is quickly show you, like in the code, like from my side, how I did the implementation. There is not much surprise. I tried really to be close to what we had set up for these local contributions. Have the same expressions implemented. What I quickly wanted to show is, for example, when we solve the linear system, the matrix form, then we do have that inverse of the mass matrix that we do. And I wanted to quickly show you that part and discuss it a little bit. Is that okay? And if you have some other questions, please just go on. We can just discuss whatever you want.
Can you hear me?
Yes.
Have you already looked at the codes of 6, right? Or not?
Not yet.
Oh, okay. Because I have some puzzles about it.
Okay, good.
Okay.
So let me show you the MATLAB code. Is that okay with you?
Yes.
Could you see the MATLAB window or not?
Yes.
Good. So you see this part here, homework 6.
Yes.
Shall I try and make it bigger, or is it okay? Can you read it?
Yeah, bigger is better.
Maybe
A
bigger
little
is
bigger,
better.
please.
Good. Let me see how I can do that. Good question. How can we increase that?
Professor, actually
Yeah.
we can do from our computer. So there is a zoom ratio in the view option, so we can adjust. So it's no problem, I think.
You want to try that? I don't see the option where I can play
Above,
around with the
I mean,
font.
it's from our on side, from
Right,
viewer
that would,
side. Yeah, if you
that
go
would be
to
in your case, yes.
view option in Zoom.
Yes, let's try.
Yeah, I can see it bigger now. Thanks.
Yes, yes, it's no problem, Professor. You can continue.
Okay. Yeah, I don't see where I can change the font size here. Good. So if I choose just the case 1 and then play with the number of elements, let's say 10 here, and see if it actually runs. So then what I'm trying to see if we can get out the mass matrix. Good, so this would be, do you see the figure as well or not?
Yes.
Yes.
Okay. So that would be the problem A solution, where we have this harmonic initial function. And then we use 10 elements to approximate the solution for the unsteady state heat diffusion equation. So that looks pretty good when we compare against the exact solution. Now, one of the points here is interesting to look at is the mass matrix or the capacity matrix, because that's something we will see in the spectral element method, that there the mass matrix or capacity matrix, this thing here, will be a diagonal matrix. But let's see in this finite element implementation. So for the mass matrix, we have these local contributions that we assemble. So we do have non-diagonal elements that we will add to the mass matrix. And so this is then basically the assembly part. So let's see if I can do that. And just see if I get the output from that. Yeah, that's the figure. So this is, let's say, one of the mass matrices, the global mass matrix or capacity matrix. And you see we do have these off-diagonal elements as well. So what happens to a matrix which is like banded, like in this case, when we invert it? Or we can say for sure the inverted matrix is certainly not just a diagonal matrix. So let's see if we can actually get that out at some point. What we want is not just the matrix, but the inverted one, because here, when we solve then, for example, for the time derivative or like the velocity case, we take the inverse of m and multiply with the right-hand side, which includes here the stiffness term, stiffness matrix. But in order for the time stepping, we have to bring over the mass matrix. So we have to invert the mass matrix. So let's see if inf m gives us something. Not sure if that runs. Okay, the figure again. But this part here, do you see that? So on top we have the mass matrix, which is this banded matrix. And now we invert it because we need that for the time stepping. And so the inverted matrix is usually a full matrix that we obtain. So as soon as we have off-diagonal elements, inverting it leads to a full matrix in general. So when we have then the inverted matrix multiplying a vector or the stiffness term, we have products which involve all the elements from the force from the right-hand side vector or from the stiffness term. And this makes it now not very convenient if we want to parallelize it. So if we want to parallelize it, it would be much more convenient if we would only need the neighbor information. But here we need the information from all elements basically to make that product. So this often leads to a bottleneck, because if we do parallelize, we need them to share the information again from all different parallel processes with each other in order to then make this part here, for example, to compute that. So we have either this is called all-to-all communication. So all processes have to communicate with all other processes. Or if you want, it's no more a local product. Now think of it if it would be just a diagonal matrix. So if M would be, or the inverse of M is a diagonal matrix, then we only compute basically with a very specific element. So we don't need to have like the full vector anymore, but we only need to have the product with a very specific nodal point, global node. So it becomes then a local method. And if the point is shared between elements, then we just need to basically make sure that if we split it between different processes, that they would share the information on shared points. It's then just a neighbor information that we would need to pass. So when we do a finite element solution, often or ideally we don't actually parallelize it, but just try and make the matrix as big as we can in our laptops or in our workstation. And then we can do it on a single node and invert it. So it's still then, there is no need to parallelize it. But when we parallelize a finite element approach, then there are then techniques here which try and work around this all-to-all communication. So what the approach is called mass lumping. And mass lumping approach tries and approximate this inverse matrix with more diagonal or banded contributions. So then that you only need again to share information with neighboring partitions. Called the mass lumping approximation, where you approximate this inverse of M and shrink it down to something that is more diagonal rather than having a full matrix. But it is an approximation to it, so you lose accuracy when you do that. Just something to be aware of when we implement it with a finite element approach. This in general leads to these full matrices of the inverse of M, the inverse of the mass matrix or capacity matrix. Is that clear? Good. So it becomes important when you start going into high performance applications. Right, is often the basic question often is your method a local method or is it a global method? A local method would be, for example, the finite difference approach, would be the spectral element approach. A global method, on the other hand, would be, for example, the pseudospectral approach. And for example, this part here, we use a finite element approach. Then we will need to make it somehow, break it down into more a local version of it with this mass lumping technique. So usually local methods adapt well to scaling it up to very large problems, where global methods, they often are bounded by the size of the problem. And at some point they become not efficient enough anymore to scale up to bigger problems. Good, so now let's talk about the implementations issue. What's the issue you had?
Yeah, I have several problems about this. The first one is about the I'm just wondering if the K, F, and M matrix are always same as we do the time marching.
If they are always, say it again.
If they're always the fixed one, that means that they will not change during the time marching.
Look at, for example, the mass matrix here. So the local contribution depends on the element size and on the density times C capacity, or the specific heat. So yes, that's something that you could take out and compute only once before you start the time looping. It doesn't change.
Okay.
Density, specific heat, they don't depend on time. So yes, there's something you could start at the beginning, set up to make it more efficient.
Okay. And another one is also about the the local force vector, like the FE here.
This one, yeah.
Yeah, maybe a little bit scroll down to the about the boundaries part. Yeah, because in the PDF files we say that if the n equals 1, then we have to set values to the f1 and f2. But why is there only one fe1 here?
Right. So let me see if I have the expression. Let me quickly show you the PDF again. Because the contribution is only on a single node that you have to add here. And if you look at the PDF,
yes, it's pretty similar to the homework 5, but
right.
I didn't figure it out yet.
But you see this part here.
Yes.
So this means it's a Kronecker delta function, which is only one for the point A1. So it's only one for a single node. So for element 1 on nodal point 1 in your local reference element, there you have to add this Q0 factor.
To F1 or F2?
This will be F1.
So
you are in the local reference, and on this boundary, you only have it on the F1. Right.
So
it would be different for this guy here, for the other boundary option. So you see the first one here, it just adds this Q0 on this leftmost point that we have.
Yes.
And then for the other part, basically it's trying to compute this product here. So it adds as well on the on the first local node, but then taking into account these contributions from the second point as well.
Professor, can I say that for the first element here, we have to change the F1 and F2, right? Because then we can say that delta 21 equals 0. So we cancel it. We don't mention it, right?
Right. So you have this Kronecker delta A at point 1.
Yeah.
So if A is 1, then this is 1.
Yes.
A is 2, then this is 0.
Yes.
But you only have to keep it on 1 point. Yes.
Yes. But also for the last element, if we set A separately to be 1 and 2, then we will have to change two values, F1 and F2, because they're not 0, right?
Yes. But now you have the issue with the last point that we keep fixed. So then you have to see which part of your local force contribution actually comes to the global force vector.
So we only consider the K12 here, not K22.
Right. Yes.
So is it always the same for all the case that we have boundary conditions?
No, this is specific to this setup that we have here because of these boundaries at top.
Okay.
So it's due to the boundaries here because we keep the boundary on the right-hand side. We have this Dirichlet boundary and keep it at a specific temperature, which makes it that we have this sort of function expansion then. So where we use now the number of elements and then add like a last shape function to impose that boundary condition.
Okay.
But you see F here, the global force has the number of element entries is not the number of element entries plus 1. So if we wouldn't have that boundary, then there would be a different. So, well, if we don't have a boundary, then you don't have these additional terms that you have to add, but you really just have this part here that would stay, which you would have to evaluate on both nodal points in your reference element. But now adding it on this point here is because the way how we make this expansion, because of this expansion here.
Okay.
It's specific to the boundary condition and specific to the way how we expand the function of for which global element you need to have which local contribution.
Professor, I have the last one question.
Mm-hmm.
That is related to the half-space cooling.
Mm-hmm.
Because I noticed that in that part we have theta, we have t, and actually I don't know which is our target and how to describe them in our codes, because I'm now a little in a mess about it. So theta is our target, and we need to compare to the theta.
Right. Yes, we have this sort of non-dimensional temperature. That we use to solve for. So theta is a non-dimensional temperature. Where could I show you that? Yeah, here I just called D the solution field. It's not necessarily something that I wrote out here in the implementation. So for the let me try and see if I find that. For the half-space cooling model, we make this substitution of variables. That at the end we want to solve for the non-dimensional temperature theta, which is this ratio of T minus the mantle temperature divided by the difference between initial and mantle temperature. And so that becomes a non-dimensional unit, the temperature unit that we solve for. I think it's mostly mentioned in the slides now.
But in the equation there is T, but I guess if what we wanted to compare the half space cooling part with the harmonic part, then the D is just the T in the equation.
The D would be the theta in the equation. Let me quickly show you the slide. When you look at the slide here, so here you see the half-space cooling model, and the part mentioned here is basically the equation that we have for the non-dimensional variable for theta is exactly the same. So it's this non-steady state heat diffusion equation. So we solve for D, which is in this case theta.
Okay, then I got it.
Okay.
Okay.
Does
Thank you,
that
Professor.
explain the question? You see, we compare them against the exact solution against this one.
Yes.
But the boundary conditions, they are on opposite sides, basically.
Okay, it is clear now. Thank you, Professor.
Okay. Good. So is there some other question or discussion point about this homework 6? No more questions for it? Good. Then what I would do is we look into homework 7, and I will show you the slides for that part. And maybe just quickly before we attack the slides, list the bullet points that we have when we implemented with the spectral element method. Just to make us aware of what the single steps are when we implement it with the spectral element method. For that, I just really want to go quickly through the notes here. So let's see if we get this to run. Good, you should see the notes about our new upcoming homework with the spectral element method. So again, the equation is the same like in homework 6. So we look at the unsteady state heat diffusion, where we have this thing here. So what is the first step in order to solve this with the spectral element method? Step 1. Suggestions?
Find the weak form.
Weak form, yes. Good. Let's do the weak form. So the spectral element, like the finite element method, is a weak form method. So first step is write this down in a weak form. Then we have these integrals, rho c t dx equals, and then on the right hand side you see we use this integration by parts to end up with expressions where we have first order derivatives of test function and temperature fields. And this becomes the stiffness term, and then the boundary contribution. So again, this would be the mass matrix or capacity matrix. This will become the stiffness matrix, and this would be the boundary. Next step, second step,
Shape function.
a shape function. Hey, very good. Well, we're fast in progressing. Shape functions. So what shape functions do we have? We use these low order, actually linear shape functions in this case. So which looks something like that. N1, N2 are our linear shape functions which deal with the mapping. So it goes to our reference element between -1 and +1. And then we use these linear shape functions N1 and N2. And in this case, what we chose are these degree 1 Lagrange polynomials. We could also just say it's linear shape functions that we use. But you see N1 and 2, they are specific also to the range that we set. We set the reference range to be between -1 and +1, which then leads to these two shape functions, N1 and 2. If we would define our reference range to be between 0 and 1, for example, then the shape functions would look different. But you can look up the notes to see how we actually define these coefficients of a linear function, such that they obey our reference range, for example. Good. Now we have the shape functions, and what we finally need is the Jacobian, which is defined as being the derivative of x with respect to xi in the local coordinate, which for these shape functions becomes, for example, 1/2, and then just as an example, use the x2 minus x1 points, nodal points, where we have x of -1 would be this point x1, and x evaluated at +1 would be the second nodal point, x2. These are global nodal points. You could also think in terms of e +1 minus xe. This would be e and e +1, for example. Those are just the points in the physical domain, in the physical space. But so this gives us the Jacobian that we can evaluate. Then third step,
Basis function.
the basis function, yes. Excellent. And this is different to the finite element approach. So see, we use now higher order basis functions for the function expansion. And in particular, we use these Lagrange polynomials, L alpha of degree n of psi. So here, these are these Lagrange polynomials. I'm pretty sure that after the class next year, you have forgotten what kind of polynomials we use, or what the name of these polynomials were. Because we keep on talking about Lagrange and Legendre. We have Lagrange polynomials and Legendre points. So at the end, you will forget both of them and just remember maybe that we use higher order basis functions. Now that's fine. But so the basis functions are these Lagrange polynomials of degree n. The degree is often higher order, meaning degree 4 or higher. And this is a main deviation now from the from the finite element method. So we start separating shape functions and basis functions. For the finite element method, we didn't separate them. We use both shape functions for the mapping and also for the function expansion. So basis function, good. What would be the fourth step?
Is it mass matrix?
Right. So in principle, we want to compute the mass matrix form. And to do so, we need these local contributions. So fourth step would be figure out what are the local contributions. Local meaning on the local level. So for our reference element. And for that, we have the mass matrix, local contribution. And that's something we wrote down last time. So we have a local contribution on point beta 1 is then equal to these integration weights omega hat for that point, GLL point, times rho evaluated on that point, times the specific heat for that point, times the Jacobian for that point. This will be the local contribution for the mass matrix, local contribution for stiffness matrix. We also figured that out. Here we had this K beta 1 gamma, for example, element. Was this summation over alpha to n omega alpha hat conductivity at the GLL point. And then we had these derivatives of the Lagrange polynomials, the L prime. evaluated at the GLL point xi alpha times the derivative of L gamma n evaluated at that point times the Jacobian times these derivatives of xi with respect to x evaluated at xi alpha. And now this should be squared. Oh, running out of space. See if I can move this a bit over. Times these derivatives squared. So then once we have these local contributions, the idea is to have our system of equations, which would look something like that, of t beta 1 t equal to the sum of k beta 1 gamma times t gamma t. So that would be our system of equations. Next step. With these local contributions.
Setting the boundary.
Yeah, let's say good boundaries plus boundaries. We have them in our notes from last time as well. But what will be the next step after having our local contributions?
Assembling.
Assembly, exactly. The assembly stage. Assembly. And for that we use this indexing from local to global array indexes. So think of having some elements, and then our GLL points. Let's say for degree 4 basis functions. Then we have these GLL points, which locally we can just index from 1, 2, 3, 4, 5. And then the next element, 1, 2, 3, 4, 5, etc. And globally, we just keep on indexing here, 1, 2, 3, 4, 5, 6, 7, 8, etc. And so on. So let's say the global index is J, the local index is I. Then what we need is an array like iglob, we often call it, which takes the element number, I element, and the local GLL point I index, and stores the global index J in that one. So now if we are in element 7 on the local GLL point 3, we know what the associated global index for that node would be. So now we can assemble the global matrices with that sort of indexing. So that belongs to the assembly stage. So again, this will lead to the global matrices. And the mass matrix you see from above, the local contributions, they don't depend on time. So you can assemble a mass matrix, for example, ahead of the time loop. You only need to do it once. So then we have the global mass matrix, the stiffness matrix, and the right-hand side vector F. So this would be a vector. And M, this will be a diagonal matrix. Good, what's the last step in order to solve it? Step 6 and final step. Suggestions, ideas? What do we do with these global matrices?
Time marching or?
Right, yes, we still need the time marching. And so what we use here is this called predictor corrector. Predictor corrector scheme. Which looks something like that. We have Tn plus 1, then Tn plus 1/2 delta T, the time step size, times the derivative Tn. And we have in the first predictor step set the derivative to 0. Next step is we evaluate Tn plus 1, the derivative of it. It's going to be this 1 over m times the right-hand side, which is the stiffness plus the force terms. And then with this, we can update or correct the temperature field with this correction term, 1/2 of the derivative of T. So this would be the predictor step. And then this is a corrector step. Good. What you see is that it's very common since we started with the pseudospectral method. We keep separating the degrees and the schemes for time and space. So we keep doing that with the finite element method, with the spectral element method, etc. So the actual spectral element method part, it really just deals with the spatial derivatives and the spatial approximations. But the time stepping, which deals with this time derivative or time approximation, that is like based on a different scheme. And this predictor corrector scheme is, if you want, is equivalent to a finite different central scheme, if you want. So the choice of the time scheme could be made different as well. We don't necessarily need a predictor corrector scheme like the one we use here. We could just use, for example, a finite different central scheme to approximate the time stepping and then write it down that way. So that makes the schemes then a bit more tricky to evaluate, because now we might have a different degree of accuracy for the time scheme than the spatial scheme. And this is very common, for example, in seismology to use, let's say, a degree 2 second order time scheme together with a degree 4 spatial scheme. So even if you would just implement it with finite difference approaches, you might want to have a higher accuracy for your spatial derivatives than for your temporal one. Seismology, that's very common to do. And so all these variations that we saw now with pseudospectral, finite element method, spectral element method, they mostly attack or only attack actually the spatial derivatives to approximate them numerically with these variations of the method. The temporal scheme kind of keeps being a finite difference scheme that we apply. So the advantage when we use a predictor corrector scheme is often that we can use the same field array and just update that one rather than having a copy of it that we would need when we use another, let's say, a simpler finite difference scheme or whatsoever. You might then need for a finite difference scheme not just 3 copies, but you might need 4 copies or 5 copies, etc. So something that we always look for in these schemes is how can we shrink down the memory requirement, for example. If you can do it with 2 fields rather than 5 fields, then that's more convenient numerically. So that's why we, for example, here we went over to predictor corrector schemes. At some point they become a bit more elegant when we can use the same array and just update the array rather than having a copy of it, and we need to have 2 or 3 copies then in order for the timing and time stepping. So that's the only reason why we keep changing these temporal schemes. No good. So last 10 minutes, we can quickly look at the slides. And the slides for the new homework, so homework 7. Let me quickly show you that. Good. So you see the slide? So the unsteady state diffusion equation, you have it on top, the strong form with the boundary and the initial condition. So we set out the weak form. We have it here again, together with the function expansions. You see the unknowns, our T alpha, they depend on time. So when we write this down in a matrix form, the system would look something like that. If we don't have a force term, then F actually would be 0. So it just becomes a homogeneous equation that we would solve. And then we basically solve for D, which is the vector with the unknowns. Then we have the mapping. So here we use these linear shape functions, the degree 1 Lagrange polynomials. Give you the mapping from the physical domain to the reference domain. And then we do the actual interpolation of the integral values, which is the quadrature. The quadrature introduces these omega weights, these omega alpha weights. So we use a GLL quadrature rule, the Gauss-Lobato-Legendre quadrature rule, which comes with these specific omega alpha weights. They are set by the rule that we use. This is how these polynomials would look like for degree 4, for example. For degree 4, we have these 5 GLL points per element, per reference element. And the locations of these GLL points are very specific. They are basically the roots of a characteristic equation, which involves the Legendre polynomial. So we have Lagrange polynomials together with GLL points, which gives us this property of the, you have here the Lagrange polynomials property, the bottom, which is this Kronecker delta function. So the polynomials are really just one at the specific GLL point associated to the polynomial, and 0 on all the others. Good, this would be how you would find the GLL point position. So you would look for the roots of this characteristic equation, and the roots give you the point location. But this is basically all set up at the beginning. When we choose a certain degree, then we can figure out what are these actual positions, the GLL points for the reference element, and start from there on then. Now we have the local contributions here for the mass matrix or the capacity matrix. Because of that Lagrange property with the GLL points, this boils down to having only diagonal non-zero entries for the mass matrix. Then we do the same for the stiffness matrix. It becomes then a banded form. And then we have this equation set up in a matrix form with a mass matrix, stiffness matrix. And the boundary terms, that belongs to the right-hand side vector. where we again just impose the boundary term on the first and last element, for example. But here you still keep the summation because it involves derivatives of the polynomials, which will have non-zero contributions from all GLL points within your local element. Then comes the assembly stage with this matrix, like the location matrix, to go from a local index to a global index. And with that, for example, the assembly for, let's say, the mass matrix or the capacity matrix would look something like that. Where you have a loop over elements, then a loop over the GLL points, and you compute what the local element contribution is, M local, and put this, assemble this into the global mass matrix, the M global part. For that, you would use this location matrix or this iGlobe matrix. You see, because the mass matrix is just a diagonal matrix, we actually just use a vector for that. You can just store it. You only need to store the diagonal elements. The same like storing a vector. And then the scheme here, you have this predictor corrector scheme where you start the time loop with this predictor step, and then you have to correct it, and for that you need to solve this right-hand side or solve the system for the correction step. And again, this scheme can be a bit simplified because you see we start with the T dot, so the derivative of the temperature field to be 0. So if you look at your corrector step at the end, the actual solve that you do just gives you actually then the derivative T dot for that n plus 1 times that. Good. And then the results should look something like that. If we keep evolving basically with our time, you should approach this steady state solution for very long times, then we should see approach to that. You can again play around with the element spacing if you want, but also with the element properties. So if you want, we can choose different material properties and then see how that would basically affect your solution. And again, when you step long enough, you should reach the steady state solution. Good, that's it. Do you have questions about that? Not much. Could you see that when you implement it, again, I give you the templates for it, but then you see how actually the implementations change when you go from a finite element implementation to a spectral element method implementation. So we use exactly the same equation, but just change now the numerical method in order to solve it. So that's the pretty much the idea of this class. But by doing it then by yourself, you notice that one implementation then becomes more involved than another implementation. So one method you get a feeling for how much work is involved actually to implement it. And we kind of keep increasing the complexity of the method now. So we started with a very, let's say, simple finite difference approximation, numerical method, and then keep adding now more and more complex methods. So this is pretty much the most difficult one for this class that we add. Then let's see about the finite volume stuff when we come to that. But so the initial outline of this class was really going from finite difference, showing you two different strong form methods, and now two different weak form methods. And you see by implementing the same equation with these different methods, how actually the implementation keeps more and more, like the complexity keeps increasing for these methods. But it comes with some benefits to it. And here for the spectral element method, one of the main benefits that we find is this global mass matrix, which then becomes diagonal. And that leads itself very well to like high performance computing and to very large problems, because it becomes trivial or kind of simple to parallelize these kind of problems. Good. Any question from your side? Everything clear? So I put this on GitHub, the new homework 7. You can start attacking it. I would say we give it another week, no? So until Sunday? No, what do we have? Yeah, Sunday. Let's say Sunday in a week. Try and finish that. What I want to come to next is the wave equation, how we implement the wave equation with the spectral element method. So we do unsteady state heat diffusion and the wave equation with the spectral element method. And then after that, we can go on to the finite volume and to end with that. We do have a little quiz that we can do about these 4 methods that we looked at so far. It's mostly for you to see how much you understood about that. And we could also look into like one of these bigger codes, like the spectrum codes, for example, how you would run such an example. Let me think about how to set it out for the last, don't know how many lectures we have left. So I think the semester ends within a month. So we should have now the four more weeks that we can go. So we can discuss that next time, how we want to actually lay out the rest of our class. Is that okay with you? Good. Then let's stop here. Let's call it a day. And we would see each other next Thursday. Is that good?
Yes.
Okay, good. Good timing then. Good. Bye. See you, everyone. See you next Thursday.